statistics after quantum quenches as hydrodynamic fluctuations.
Thank you, Elijah. Thank you, Nadav, for reminding about that. And thank you very much for the invitation to this nice conference. So, yeah, this talk is probably a bit different from like average talk of this conference. I hope, so feel free just to ask anytime. And yeah, so this is work in collaboration with other people at King's, in fact. So Benjamin Doyon is a professor at King's, and David Horvat, who is a postdoc here. Okay, so this is the outline of the talk. So in the first part, I will spend actually some time here talking about, in general, fluctuation and the relation to full counting statistics, and what we know about that already. In particular, we'll say something more specifically in the ballistic regime. And then the second part is to do more about our work, which is about full counting statistics in some auto-equilibrium setting, in particular after quantum quench, which I will introduce. So, okay, we can start with the first part. So let me start with some introduction and motivation. So this talk is about large-scale fluctuations. And we want to study them in the context of many-body system, let's say for now, to stay general. And what is true is that all many-body systems, basically all of them, admit at least a few conserved quantities. So the easiest thing you can think about is a gas of particles, where a particle number is conserved, for example. But of course, if you now restrict one of these conserved quantity of conserved charge, we'll call it as well, to a subsystem, this is clearly not conserved anymore. Again, in this example, just because a particle go in and out, so it's not conserved. And so this restricted quantity is not fully characterized by its mean value, but fluctuates instead. And to fully characterize it, we need to know all its cumulants, which are related to the connected correlation function of endpoint correlation function of this quantity. And such cumulants are generated by this object called full counting statistics, which is this function f of lambda, which is the logarithm of expectation value of e to the lambda, this charge restricted to the subsystem. And this quantity, as you may know, so it generates all the cumulant by Taylor expansion, or just deriving with respect to lambda, putting lambda equal to 0. So why are fluctuations interesting on a large scale, where here by large scale I will mean both like in space and in time? It is because they encode universal properties, okay? So, for example, as I will say in a while, at equilibrium, they don't depend on all the details of the system itself, right? But just on thermodynamic function like macroscopic variables. Okay, and basically, most of what we know about that is based on the large deviation principle. So the statement of the large deviation principle is that if you consider an extensive observable, here I mean extensive in a generalized sense, so this observable just scales in some way with the space x and time t, then the probability for this observable to take some value which is different from its mean value, basically decay exponentially in this way, okay, with this scale here. And this function is called as a rate function. And this is like the main object we would like to study, but in many cases it's actually easier to study instead its Legendre transform, which is called full counting statistics, okay? And in this large x and t regime, this is defined in this, through this limit here. So without being very precise, let's say that in general for an ergodic system with a local interaction, such a large deviation principle is expected to hold, but in fact it's rarely proven. And especially if you are looking at hydrodynamic observable like charge densities or current, as I will be interested, this is even expected to hold even more widely in a sense. And also observation though is that So this principle gives, if you want, the form, right, both of the probability and the full counting statistics. But actually, if you want to compute them explicitly, you need to combine it with other tools, right? So it's not enough. Okay, so and to say a bit something more about what we know for now about these full counting statistics, let me be a bit more specific than generic many-body system. So now we restrict to one-dimensional homogeneous quantum system with local interactions, and we assume that this system will, for this system to have n conserved quantities, which are assumed to be local or quasi-local. And in particular, what I mean by that is just that these charges are written as the integral over some density, and this density satisfies a continuity equation with together with this to the associated current. And in this audience probably is not, I don't need to say, but n in general is, so the number of conserved quantity in a system in general is small, right, 2, 3. But for integrable system, instead, it's infinite. And a special subset of states that will play like a main role for what I'm going to say later are steady states. So those are the states that are expected to, at some point, to arise after some long-term dynamics. To this state, so part of these states are the so-called maximal entropy states, okay, which are, for example, Gibbs ensemble or generalized Gibbs ensemble for integrable models, and they are specified by a vector beta, which whose component is the same number as the number of conserved quantities, and formally these states are defined by this density matrix. So according to the fact that they are maximal entropy state, they're just the exponential sum over I beta I qi, with this beta I playing the role of a Lagrange multiplier. But also, these are not the only ones. So also steady state are also not just equilibrium steady state like this kind, these GGs, but also non-equilibrium steady states, or NES, which are states a bit more general that can sustain persistent non-zero currents. So they will also play a role later on. Yes, and so what do we know about full counting statistics in different settings? So let's start with the easiest problem, which is considering some static quantity on some large region in some steady state, or more specifically at equilibrium. So in this case, it is known. Actually, I mean, in different contexts, in different communities, but since quite a long time, that in this case, thermodynamics is enough to describe full counting statistics. And what I mean by that is the following: is that if you consider a charge restricted to some large subspace, so here 0x. And you define the associated full counting statistics. Here I'm assuming that the scaling is just, so Q of x is just a scale like x itself. Then this is just given by a difference of free energies, right? So in this sense, it's just characterized by the thermodynamic properties of the system, where you see in the first, so here I'm just highlighting the fact that the difference between these two free energies, that in the second one, the Lagrange multiplier associated to the charge I'm considering is shifted by lambda being this parameter entering, this counting field entering in the full counting statistics. Yeah, and this free energy, of course, is related to the steady state I'm interested in this way, right? So this is the relation. Okay, the next step is what about, so we consider dynamical quantities on a larger time interval, but still in a steady state. So in this case, I mean, thermodynamics, of course, since we are starting to go towards the dynamics in a sense, is not enough. But in some cases, it's known that now what we need instead is just the hydrodynamic data. And so more specifically, say that you want to look to some charge passing through some interface like x equals 0 for some long time, then the full counting statistics take this form, where now here I'm allowing some more general scaling with time, and the scaling here is of course fixed by the transport properties, basically, of the system one is looking at. So in particular, if a system sustains ballistic transport, this corresponds to alpha equal 1. And this is the case, for example, for integrable models, that what we expect, ballistic transport. And in this case, so in order to know this quantity, what we need to know is Euler hydrodynamics, and so the explicit form of this quantity is given, so using this Euler hydrodynamics by the so-called ballistic fluctuation theory, which is quite a recent framework. I will talk about that more specifically in next slide. Another important case is for alpha equal 1/2, which is the diffusive scaling. And in this case, the theory that allows us to fix the properties of these full counting statistics is MFT, or macroscopic fluctuation theory. And then, in general, transport is called anomalous for generic values of alpha. For example, alpha equal 1/3 is the so-called KPZ scaling. But in general, for generic alpha, the large radiation principle itself can be broken in some case, so we don't have like results for generic alpha. So the following step is that what I was talking about here was always looking at expectation values in a homogeneous steady state. But in fact, one can extend at least to slowly varying states, okay? And this is because, at least locally, they are still maximal entropy states, and so we expect hydrodynamics to still hold, okay? Instead, a big step, like with respect to this example here, is if we ask ourselves, what about if we are truly far from equilibrium? So in this case, mass less is known, and so our work, is in this context. So this is what I will talk about in the second part of the talk, basically. But before that, I want to say just 2 slides about. We're still in the context of steady state, or at least a slowly varying state, in the ballistic regime, because these I will use in the following. So again, consider one of the charge of a system with the density and the current given by Q and J. So in the previous slide, I talked mostly just about either a current in a big interval, or a charge in a big interval, or a current in an interval of time. But more generally, one can consider, it's convenient to consider what I will call as generalized 2 current, which is an object. Basically, I can consider a more general path from 2 points in space-time, 0, 0, and xt, and define this object, which basically, if you just consider an horizontal path, this just goes back to the case of a charge in a subsystem, and the vertical path instead gives just the current in a time interval. But you can consider this more generic object. And in the ballistic regime, so we know that we expect time and space and time to scale in the same way, so we can introduce a unique scale, L. And we expect this generalized 2 current is delta J to scale like L, and therefore the full counting statistic in this case is defined as the limit of the scale L going to infinity. So what this theory that I was mentioning before, of this ballistic fluctuation theory, gives is a prediction for this full counting statistic f of lambda. And just give you the result mostly. So this is the result is basically an integral over a flow in lambda. So we have these generalized 2 current, so evaluated in a state which is lambda dependent, and in particular is nothing but the steady state we're interested in. So multiplied, so biased by this e to the lambda delta j. So maybe it's more useful to look at an explicit example. So instead of considering a generic path, consider a segment path of this kind. In this case, f of lambda takes this form, and here you can see clearly that basically this is completely fixed by if we know the expectation value of j and q in this state. And so we only need, so these are exactly what I mean by hydrodynamic data. So if we know the hydrodynamic theory, we know this expectation value, and so we know this f of lambda. And this is the case for integrable models, because in this case we do know the hydrodynamic theory associated, which is called what is called generalized hydrodynamics. I won't tell much more about that. Instead, I just want to make an important observation, which is the following. So this result, and also the ones in the previous slides, basically we were all the time talking about steady state or maximal entropy states even. So why was that? So here, for this result to hold, for example, a key assumption is that along the integration path, one assumes that there are no strong correlation among those points, okay? And this is just true in most steady states. That's why most of the results that we have are in this case, okay? This instead is not true out of equilibrium, which is what I'm gonna tell now. So now in the second part, I'm gonna talk instead about how to characterize this full counting statistics out of equilibrium. So an easy way to go out of equilibrium is to consider this quantum quench protocol. Yes?
So what's like the status of the statistics?
In which, well, I mean, this was meant to be kind of the status of things. So in steady states or slowly varying state, okay? This is kind of we do understand. So if you just look at equilibrium, this kind of old results, though in different communities were understood in different times. If you go to dynamical quantities, it's more recent results, in fact, already, and even more recent this extension to slowly varying state. Instead, out of equilibrium, we don't know much, so what I'm going to talk about is about that. So what our contribution, our basically the paper that I was mentioning at the beginning are about that. This a specific out of equilibrium setting, which I'm going to introduce now.
Yeah, but my question is like, is there proof of some system that it's the right description?
Like, it depends on how rigorous you mean. No, I mean, yeah. If you want, well, yeah. So sort of like so. This paper are a sort of rigorous paper, for example. Out of equilibrium, sorry, for dynamical quantities, yeah, I mean, like exact result, but not rigorous, I would say, okay? Exact, but not rigorous. Already, if we go to currents, for example. But I mean, some results, for example, are in this review, and which is quite rigorous. Okay. Yes. Yeah. I don't have a specific answer, to be honest, to that. Like, yeah. It's also a bit model dependent, and whether there are specific results. But I would just say that at equilibrium, in steady state, the situation is clear what's happening. Okay. Instead, out of equilibrium, it's very different, and I'm gonna now explain why. What is the big difference here? So first of all, for those of you who might not be familiar with, let me just say what is the so how do we generate the out of equilibrium dynamics, basically. So the easiest way of doing that, that's why we consider that, is through a quantum quench protocol. So the most general definition of that being that we initialize the state in some initial state psi 0, which is not an eigenstate of the Hamiltonian which governs the evolution, and not even any superposition of few eigenstates, so that really when we let it evolve, or like according to Schrödinger equation with the Hamiltonian, it will really evolve. And what we know in general about quantum quenches is that at long time, thermalization or generalized thermalization, depending on whether the model is integrable or not, is expected, meaning that local observables are expected to be described by a steady state. So here it's important that this holds for basically for one point function, okay, so local observables. And instead, the same steady state is not enough if we want to describe fluctuation. This is because steady state usually they don't have the information about long-range correlation. Okay. On the other hand, long-range correlation are expected to arise after a quench, and an easy way to visualize that is to think about this initial state at time 0 plus, let's say, right after the evolution has started. This can be seen as so the initial state can be sort of seen as a source of entangled pair of particles. So this is particularly true in the case of integrable models, where really you can think really about the state as being a source of pairs of particles with opposite momentum. This is called also quasi-particle picture. And this is, this is also true specifically for what we refer to as integrable quenches, which means quenches from specific initial states where the only correlation are due to these pairs. So more generally, you can have some multiplets or some other kind of correlation, right? But in integrable quenches, they really have this structure here, and they can, like, in fact, written in this way, where kind of a la Bogoliubov, where it's clear that it describes particle with opposite momentum. But okay, if we want to be a bit more general, even if we are not talking about integrable models, the quasi-particle concept can be replaced by the concept of hydrodynamic modes, but okay, I won't talk about that. Okay, so let's come to the full counting statistics after a quench. What can we say about that? So here I will consider just 1D interacting integrable models, and I will restrict to these integrable quenches, which I just introduced. Though, many things can be generalized in general in the presence of ballistic transport. And as charge, it's good to think about the particle number, though again, it's easy to generalize to local charges. And the object of interest in this case is this one. So we are interested in studying the given charge restricted to some subsystem X after some time, large time t after the dynamics, starting from the state psi. Okay? And we are interested in ballistic regimes, so both x and t scale like L, and that goes to infinity. So the easiest regime is where, L and t are both large, but still x is much smaller than t. Since time is large, basically one can assume that psi is relaxed to a steady state. And as I said before, this is basically at this point, everything is fixed by thermodynamics, and this full counting statistics is given as a difference of free energy. Where x and t are like comparable, of course, is the most difficult regime. Instead, our result that I'm going to talk about in the next slide is about the regime where t is much smaller than x. So we are basically here, right? So this is the easy regime. This is like an intermediate regime, which is the most difficult. And this is what we're going to talk about, where time is small, but it's still macroscopic, okay? Because we are in this ballistic scaling. And so, and this makes the problem non-trivial, because in this small time, we cannot forget about this correlation that I was mentioning before. So I will start by showing and comment and make some comment about the result, and then I will go quickly through like how to derive it. So what we can show is basically that this full counting statistics takes this asymptotic form. So you see there is a linear term in x plus correction that just depend on x, a linear term in t that just plus a linear plus correction that just depend on t, plus a term that goes to 0 when x goes to infinity for every time. And the most interesting object is basically this coefficient in front of the growth in time, which is what we can characterize, in fact. And it turns out that this quantity here can be seen itself as the full counting statistics of the current corresponding to the charge we are originally interested in, but this is evaluated in a non-equilibrium steady state. Okay, so and this is the picture to understand what is this non-equilibrium steady state. So the non-equilibrium steady state, this nest is what emerged here at large time along this ray x equals 0 from an inhomogeneous bipartite quench, basically the situation where on the left we have our original initial state psi, and on the right we have a biased version of it by e to the lambda half q, where q is the charge of interest. And so if we just join these two systems, so some dynamics will happen, and we expect here some nest to emerge. And this is the nest we are talking about here. But the physical intuition is also that one can think as follows. So one can think that this vector psi after some time will evolve to a GGE, and the same is true for this other state here. Will evolve to another GGE here, and these two GGE now, if you let them evolve, they also will generate a nest there, and so the two nests are the same nest basically. In the case of integrable quenches, we are also able to characterize explicitly what is this GGE of this bias state here, which is the original GGE of the state psi plus 2 lambda q, the charge, and this can be shown using quenchaction methods. But an important consideration, an important feature of this result is that we started by considering the full counting statistics of an homogeneous problem. So the system is translational invariant, and we want to study just the charge after some time. And in the result, we end up instead, so in our result, we end up instead with an inhomogeneous setting, okay, which is a bit odd at this point, so it's not clear where it comes from. Hopefully it will be clear through the derivation, but this is an important, an interesting observation. And the other thing is that if we assume that in this nest there are no long-range correlation like in time, then you can use this ballistic fluctuation theory even if you are not like at equilibrium. And in this way we have an explicit expression for this F dynamical. And it turns out that this reproduces a conjecture that was put forward for generic integrable models, but coming from a completely different approach, which is known as space-time duality, which is at the level of a conjecture, but was shown explicitly for a model which was also mentioned yesterday, this cellular automata model Rule 54. What is interesting, I think, of our work is that, so two things mostly. One is that we derive this result just using very simple hydrodynamic-based arguments, which makes kind of a bit the physics more transparent. And the other thing is that, so this was a general conjecture for all integrable models, but in fact, through these hydrodynamic-based arguments, we can show that there are physically relevant cases where this formula is not exact, in fact. So the conjecture is not true. It's not true in general, but I won't have time to discuss that in this talk. So yeah, so in the remaining 5 minutes, I will just sketch basically how to get to this result, okay? So the asymptotic form is kind of, it's sort of simple to understand. It's just, so this is the log of that is the quantity we're interested in, right, this f. So we just multiply it by the same quantity but at time equals 0. And if we just using large deviation principle with a linear scaling, which is typical of the ballistic regime, so is what we expect. So this bit is expected to give the linear term in x, and this term is expected to leave the linear term in t, okay? So this just gives our asymptotic form. And with the proper limit, one can extract these two coefficients, which were appearing in the formula here. In particular, this ratio here of the charge at time t over the charge at time 0 is what gives the dynamical bit that we are interested in, okay? And specifically, the limit is first x going to infinity, and then time goes to infinity. So, okay, so the first point of this hydrodynamic argument is the following. So the main problem for doing this calculation is that accounting for this long-range correlation in a direct way is difficult, because all the results I showed you were based on the fact that there are no such correlations, okay? So the idea is that, the main idea is that if we are able to avoid them somehow, then maybe we can still apply ballistic fluctuation theory even if we are not in a steady state, okay? And if we look at charges, this is possible in the following way. So we can use the continuity equation to turn this path here, describing the charge at time t in an interval x. We can using the continuity equation, we can just deform it basically as we want, and in particular we're going to deform it like that. Okay, so we're going to write that as the sum of these 3 bits, okay? These are the 2 currents, the vertical path, and this is the charge at time 0. And the idea is that maybe along this path now, we are in such a situation that this long-range correlation do not contribute, and so we can use a ballistic fluctuation theory. Okay, so this is the main idea. The second step is to consider the large x limit, and in the large x limit, the idea is that this full object here, okay, so the exponential of these two generalized 2 current here, basically decompose into the product of the left and right contribution. Okay, I don't have time to go into the details, but mostly the assumption here is that the left and right operator commute, and that the state psi is clustering, and then basically you can write that as the product of the left and right bit, and so now you can just focus on one of these 2 bits. And now the third step is the large t limit, and the idea here is that, so now we concentrate on one of these bit here. So using some property that we call asymptotic commutativity, which is actually non-trivial, but which basically allows you to write the exponential of a sum as product of exponential and just, reshuffle them mostly. Now this object here you want to interpret as the expectation value of e to the lambda j, so the full counting statistic of the current, in this new state here, which now is an inhomogeneous state, is where this inhomogeneity comes from, because this charge here is just act on 0 infinity. So this is the state. On the left is the original state. On the right is biased by this e to the lambda half q. Okay. So we rewrote the problem as a problem of a bipartite quench in this now inhomogeneous initial state. And the last step now is that if we start now, if you imagine now our dynamics from this inhomogeneous state, and we look at the current, so the full quantity statistic of the current now along this ray, at large time we would like to replace the initial state by the NES emerging at long time. This is one step. And assuming no correlation along this path, then we can use ballistic fluctuation to evaluate that, and this gives the full result. So this is done again by there is some assumption, of course, that we do, but are very physical assumption. Mostly that so we do assume that this inhomogeneous state converge to an S there, at least for local observables, and that this initial state itself, if we look at time correlation of current at different times, they decay fast enough, where fast enough depends on the problem, let's say. And this is a non-trivial statement, actually. This is a bit the tricky part. But okay, if you assume that, then we have our full result. And okay, and this brings me to the conclusion. So we'll just summarize basically what I said. So what I showed is that by using just hydrodynamic-based arguments, we can derive a formula for the full quantity statistic of a charge at large time after an integrable quench, which is valid in the ballistic regime, in particular when x is much larger than t. And an important physical point is that the arguments show how fluctuations are related to the physics of hydrodynamic long-range correlations. And also an interesting point that I don't have time to discuss here, and I mentioned already, is that that formula that was given as a general conjecture is not that general as we think, because there are physical relevant situations where it doesn't hold, and it is modified by further long-range effects, which were neglected up to now in literature. And with that, I thank you for the attention.
Thank you very much. Are there any questions? At the back there, and here as well.
As I understood, you were talking about some universal behavior of such.
Sorry?
As I understood, you were talking about some universal behavior of some systems, but is it possible to check the statements you mentioned for some specific integrable models, like besides free Fermat's or Rule 54 you mentioned?
Yeah, that's a good point. In fact, I mean, this is one of the important, like, more interesting part, I think, but to get there, I needed all this bit. So let's say that this formula is very simple. It's based on very simple arguments, and it's very easy that it doesn't hold in many cases, in fact. So it was shown, in fact, in Rule 54. We showed like all the steps of the derivation in free Fermats, in different kind of free Fermat models, for example, assuming or not Lieb-Robinson bound. So what we show explicitly is a bit the opposite. So that so we give an easy example, which is in Lieb-Lininger, where this formula doesn't hold. So if you start from a BC initial state and you quench like in the interaction strength of the Lieb-Lininger, this doesn't hold. So the argument, many things go through. So they are quite general. The main point where this thing breaks down is this assumption here, basically. So the assumption is that in this inhomogeneous state here, one has to assume that correlation at different time along this ray, they decay fast enough. Well, fast enough depends which cumulants you want to use the full quantity statistic for. And this, in many cases, is not true, because it's not enough to assume that local observable converge to NES to say that that basically I can So let's say that even if local observables converge to NES, so in principle here you would think that you can in fact substitute the initial state with the NES, like this step here. This is like the crucial point. This is not enough for the cumulants to converge to the NES, because the cumulants are the integrated version, right, of the correlation function. So even if the correlation function themselves, they do converge to the NES, what happens is that the correction in the cumulants can give some correction in the linear scaling of the cumulants.
Okay, thank you.
So it seems like many of your arguments only use kind of like a very basic principle like a maximum entropy and a hydrodynamics. So do they generalize to higher dimensions as well?
Mm-hmm. Yeah, good question. I'm a very 1D person, I have to admit, but okay. I don't know. I mean, for example, let's say that what I know is that before going to out of equilibrium, right? So ballistic fluctuation theory does generalize to higher dimension. But here, I mean, what we have in mind is a bit of a specific setting, even if the arguments are general, but already when we talk about ballistic, I mean, I say very generally ballistic transport, but in practice, right? In practice means the integrable models or free ferments or specific observables, right? So it's the arguments are general in a sense, but very specific on another, I think, maybe. But it's a good question. I didn't really think about that. Yeah, okay. But it's interesting.
Okay, if I can, like, I also have 1D question then.
Okay.
So especially for the case of quench, like, what happens if you consider 1 plus 1D 2D CFT? 1 plus 1 DC.
Well, actually, in 2D CFT, this was already I mean, it's simpler. Let's say it's even simpler. But things should work. I mean, yeah, okay. So before going out to equilibrium, so basically, so let me go to the beginning. Yeah, here. So this kind of statement that Yara make in general, this was first understood for CFTs, in fact, by Denis Bernard and Benjamin Doyon, for example. So now what we do is kind of, I think that includes already the case of 2D CFT. So we didn't go like specifically to look about that, but yeah, I would say it's included into that. Yeah.
Any more? Can I ask one? We went on a little bit, but I'm curious. So one thing that you mentioned in your answer to the first question is this idea of decaying fast enough, or
yes,
and how that varies by operator, by theory. So can you quantify that precisely?
Yeah. So the reason why we don't
find a bound or something like that.
Yeah. So the reason why we don't quantify it that enough is because this depends what is your goal in a sense, because at the end we compute in physical terms. We're interested to the full quantity statistics because we're interested into cumulants, right? So let's say that you want to describe the third cumulant. Then third cumulant, you would need that to go with a given, at least with a given power, for example, right? But if you are interested in higher cumulants, then maybe you need more.
But does that mean that, for example, in Liebling-Niger, you might have some cumulants and fields for which this works, and others for which?
Yeah. Yes.
Okay.
It can be the case. It's just that I mean, what we had in mind, for example, was just the charges. Usually, it is just the
conserved charge.
Yeah, the U1 charge. So, but yeah, in principle, yes. Yeah.
Okay, I think that's all for now. So thank you very much.